Good morning, everyone. Welcome back to the second day of this workshop on great earthquakes. Today we will start with a session on some continental earthquakes for a change. And the session will be chaired by Eulalia Macena from University of Barcelona.
Good morning, everybody. So we will start this session with this speaker, with Jean-François Ritz from Géosciences in Montpellier.
Good morning. And first of all, thank you, Barbara and Jan, for inviting me for giving this talk. I'm going to present a synthesis of works that have been carried out in about active tectonics in Mongolia since the late 90s. One of the questions we wanted to address was the question of the repetition of magnitude 8 earthquake using a paleoseismic approach. So this work involved many collaborators from France, from Mongolia, of course, from United States and Russia, also from Southern Korea. I won't name them all, they're listed here. I just want to precise that a lot of the work has been carried out in the framework of a PhD in Géosciences Montpellier. So the phenomenon of seismic clustering along a single fault zone has been described for many years with outstanding example like the North Anatolian fault here with sequences of 9 earthquakes in the 20th century from 1939 to 1999 here. There are also outstanding features in the Dead Sea Graben, looking at the paleoseismic in the Lisan Formation near Masada. We talked yesterday and mentioned this, with 2 big clusters in the last 55,000 years. There's also a standing example of clustering along the Sandras Fault. It's a work by Weldon et al. In 2004, describing a sequence of 6 earthquakes in a period of time of 300 years, suggesting even that the slip along the Sandras Fault would have been multiplied by 3. And there is also a regional cluster involving several faults. Again, in California, within the East Californian zone, the question linking Landers earthquake in 1992 and Hector Mine in 7 years later. In the paleoseismic records, Rockwell et al. Describe also clustering phenomenon in this same East Californian zone. Nur and Klein describe earthquake storms in the late Bronze Age in the Eastern Mediterranean region, and Syros also in the same region, a clustering phenomenon between the 4th and the 6th centuries. More close to us in Italy, of course, we all think about the seismic activity since L'Aquila earthquake until last year with the 3 earthquakes, Norcia, Mazzaretta, and Perugia, and also investigation about past earthquake by Benetti et al. Within the Fucino fault system have described this kind of phenomenon. If we go in an intracontinental setting, in Jan Craton, we have also an outstanding example about the question of clustering linking the Kuch event in 1819, followed 200 years later by the Buj earthquake, just 200 kilometers far away. So we're going to head in Mongolia, deep inside the continental interiors, where 4 large earthquakes, magnitude 8, occur in a 52 years period. Mongolia is here. You see the magnitude 7.8 plus earthquake that occurs in the 1900s, and you see that 4 of them occur in Mongolia, among about 20 earthquakes in this region. And it started with Tetsaleg in 1905, in July 7, followed 2 weeks later by the Bolna earthquake. Then 26 years later, the Fuyun at the border with China. And 26 years later again, the Bogd fault here in Gobi Altai. And you have image here of the huge surface break associated with the Bolnai and the Gobi Altai earthquake. If we look at the strain rate through GPS measurement, this is work by Calais et al. And Vernier et al., you can see that from this GPS velocity field, we can deduce a slip rate along the fault, and you've got here east-west left lateral slag slip fault, the Bog fault, the Bolnai fault, the Tunka fault, while you have here right lateral slag slip fault in Altai. And if you stack this slip vector here, you can estimate millimetric slip rate along this fault, 1.2 along Bog, 2.6 along Bolnai, about 2 along Tunka. So we know that now that this cluster, these 4 events, are occurring along very slow-moving fault, which make them very exceptional in time. And one model has been proposed to explain this clustering phenomena through a post-seismic viscoelastic stress transfer. You have an example here of Fuyun with a comparison between the co-seismic stress transfer, just pure elastic stress, with the viscoelastic effect here, and you can see that the viscoelastic effect go much further with 2 order of magnitude difference compared with the elastics one. But the question we were, as paleoseismologists, interested in was whether we could see this repetition in the paleoseismic records. So I'm going to show you a synthesis about works carried out here in the Bog fault and the Bolnai fault. There's 2 ways to answer this question. One, which is not direct, strictly speaking. You can use a morphotectonic approach where using the slip rate, so slip rate is the cumulative displacement divided by the cumulative time in millimeter, and assuming or showing, that I'm going to speak about this in a minute, that the co-seismic displacement along this fault is constant through time, you can deduce unit time that would be regular. You just divide the time, the unit displacement by the slip rate. So to do so, you need to, of course, to map quaternary geology, you need to measure precisely the offset. So we're going to use satellite imagery, aerial photographs, and field microtopography for constructing digital elevation model. So we can do with a real-time kinematic GPS with a radio here, allowing to link the two reception. You can use kite aerial photogrammetry. You can use scanner or drone. That's for the measurement. And in terms of constraining ages, what we use most of the time is a technique of surface age exposure dating. So, in other words, in situ produced by M10, sampling quartz-rich rocks, the top of them, in the top of exposed in the top of offset markers, and of course dividing the cumulative displacement by the age of the markers. We are calculating the slip rate. The other approach, more direct, I'd say, is to date the events. So it's a trench study, so paleoseismology strictly speaking. And we're going to constrain the age. In fact, we never date the event, strictly speaking. We bracket its age. This is what we call an event horizon, the surface at the time of a past earthquake, and we're going to date the unit which is below and the unit which is above. So the two techniques usually used for this are the optically stimulated luminescence and the radiocarbon dating. So let's go now in Gobi Altai and look at this complex surface rupture, which is the Bog fault here. There's a 260 kilometers long strike slip fault, left lateral, with offset comprised between 3 and 6 meters here. You have an example of the 6 meter shutter ridges here with David Schwartz and Carl Prentice scaling the picture, the gears, Mongolian gears on the background. Here, Armando Cisternas scaling this very nice shutter ridges. The fault is parallel to the slide with about a 5 meter left lateral displacement we here in Ulan-Bulag. One of the amazing features about the bog, the ruptures compared to topography, is a very close correlation between the geometry and the kinematics of fault and the topography. You can see that where you don't have topography, there's pure left lateral, where you start to have, in addition of the left lateral vertical slip, you start to have topography moving to pure vertical slip here, and then go back to pure left lateral movement with no topography, and again, pure left lateral slip here along the Bagabog massif. So it's very complex fault with the change of geometry within which you've got restraining bands and the creation of reliefs. So this tells us something, this comparison between 1957 and the large-scale topography about the repetition of the pattern of the surface breaks. So we're going to head here, Neuenhoel, where we estimated a long-term slip rate. So be careful because the north now is on the top of the slide. So this is the mountains. You see two catchments here. And you can see that alluvial surfaces, yellow and blue, are not in line with the outlet of the basin, showing it has been shifted along the fault. And you all know how we do. We can measure, for instance, the distance between the apex and the outlets. This is S0 here, S1, S2, the three fan surface. That allow us to estimate offset. Here, for instance, S1, with quite strong uncertainties because we don't know exactly where is the apex. So a slip comprised between 50 and 140 meters. And dating the fan surface allowed to estimate 0.9 plus or minus 0.4 millimeter per year left lateral slip rate. So that the overall data we've got about the slip rate in yellow for horizontal left lateral slip rate, and in green about the vertical. You can see that the vertical slip rate are 1 order of magnitude lower than the horizontal one. And I'll come back to this picture here in this place where we've got a 1.2 plus or minus 0.3 millimeter per year slip rate. Now let's look at the slip distribution. An amazing feature along this track slip fault, but it's true about all the faults we've been studied, is that we've got a characteristic slip dislocation. In fact, if you look at the fault, so it's curved because it's I would say wide angle photograph. It's a trace line. You can see here the digital elevation model performed with the kinematic GPS. It's about a 500 meters section. You see the fault cutting through these different talvegs, and if you look at the closer here, we can see the last displacement. It's about 4.4 meter, and we have evidence for an offset which is twice this amount, about 9 meter, and an offset again which is 3rd times this. So we have observation showing that we have here is the site where we were, multiple offset that are multiple of the 1957 dislocation. You can see this is the profile along the fault. There is the distance. So you see 4, 4.5, 9, 12. And we've got several data suggesting we have then a characteristic slip. Here is the displacement, vertical displacement. Now, a recent work using a statistic approach, so using a cumulative offset probability density analysis, COPD, from more than 5,500 measurements. It's a work that's been carried out in the framework of a PhD, Robin Kurtz. So where we could show that we do have this characteristic slip distribution. I won't detail all the COPD, but you see the different peaks for the different segments. And at the end, estimating the average slip base segment, we also have a very strong suggestion that we've got a characteristic slip over 2/3 of the segment. We didn't carry out any analysis within the Bagabogd section. So now we can play, because as I tell you, if we have a constant slip and if we divide it by the slip rate, so we here, that geyser, so we have a 4.2 plus or minus 0.9 meter slip, which is 1.2 plus or minus 0.3 slip rate. We've got a mean recurrence time of 3,500 years, which in fact, taking count the uncertainties, gives this range of timing, 2,200 years to 5,700 years, which can be illustrated this way. Let's look at the paleoseismology. We've been carried out through this last 20 years about 10 trenches, 5 along the Bogd Fault and 5 along the Gurvan-Bulag thrust fault. I'm going to present what we've got here in Ulan-Bulag site, where we had very young deposits. This is a little span here, which is trapped along the fault. Here is a field view of it, and we have a repetition of ruptures affecting this recent alluvial fan. That's what we see in a trench, and very sketchily for people who don't know exactly how we do. You have, we're looking for this kind of features, full termination here, which in fact define what we call an event horizon. It represents the ground surface at the time of event, of what remains of it, because you have then another sequence of deposit above it, eroding it partly, and which been faulted a second time. So this kind of feature we are looking, and very sketchily, in this trench we could interpret 4 events: the 1957 last event, a second event, which is here, that was the event I was just showing in the previous slide, a third one here, and even a fourth one, which is not a full termination criteria, but a tilt layers with an unconformity here. We could bracket this event using different techniques: luminescence dating in blue, radiocarbon dating in black, and here are the events on the graph of time, and you see this 4 events in a period of time of 14,000 years, which give a mean recurrence interval of comprised between 3,100 years and 5,900 years, which is, if you remember, quite consistent with what we obtained from the morphotectonics approach. Here is what we've got for all the fault system. In yellow are the the recurrence interval deduced from the division of the characteristic slip by the slip rate. And in green is the age from the paleoseismology of the penultimate event. So you see there is a quite good match between these results, and they can be represented here graphically. So about 3,000 years ago, 3.5 an event, and the paleoseismology tends to show that the previous event, the pre-penultimate and the one before, were about offset in time. But if you use this different result to constrain the age, this is what we've got. So a repetition every 4,000 years of large earthquake. Let's go along Bolnai Fault now. The Bolnai Fault is this very straight linear feature, about 400 kilometers long, very different from Bogd. It's a very straight line, almost east-west, with different segments. The Tseter leg, which produced this 1905 event 2 weeks before the Bolnai, and the Bolnai, which triggered not only the Bolnai Fault itself, but also the Terraking Fault and also the Dugon Fault as well. Beautiful, large-scale cumulative features like this 500 meters long pull apart, also this huge ball tract here, which has been shifted left laterally. And the maximum slip we could measure about the 1905 event is around here, and the central part of the Boulnay Fault, it's about 9 meters. We determine the slip rates within the central part. I'm going to show just this example, which is here, which is called a GNP site. So we have an offset stream. The reconstruction allows estimating a 96 plus or minus 11 meter left lateral offset. And if we could date the surface in which is inside the river using both OSL dating and Berm 10, it's about 37,000 years. So if you divide the offset by the year, this yields a 2.6 plus or minus 0.8 millimeter per year. So that's the slip rate, that's the age, the distance within 3 sites. And the site I just shown is here, GNP, where we've got the 2.6, which is pretty consistent with what's been deduced from the GPS measurement by Calais et al. In terms of slip distribution, this is a recent work by Jin Choi and collaborators. We have this very nice distribution, which is wavy here and decreasing here from the central part, where we've got about a 9 meter to the west. And you can see already in the offset previous to the 1905 offset that we have indication for what can be described also as a characteristic slip. Here is a work that Jean and Jan presented recently in New Zealand and last summer in Ulaanbaatar. If you look at the red curve, which is the 1905 slip distribution, comparing to the blue one, which is the slip distribution on the previous event, you can see the match quite well. So here again, if you divide this characteristic slip, we're here, okay? We are where we observed the maximum slip, and where we estimated a 2.6 millimeter per year slip rate. If you divide the characteristic slip by the slip rate, this yields a mean recurrence interval of 3,400 years with this range at the limit. So comparing Bogd and Boulnay, you have a very good match with the uncertainties, of course. And we'll see what the paleoseismology is telling us. So we've been carried out a detailed study in 3 sites. They're here. You can see, for instance, very clearly the ruptures, the ground rupture associated to the 1905 event. And I'm going to detail a trench study here, a site that we call Pine Creek, where we have evidence for 18 meters, so probably 2 events here, with the left lateral offset stream, and we trench it here, the alluvial deposit, that were trapped here along the fault. The fault is east-west here. So very sketchily that the different units observed in the trench, the 1905 rupture, a second rupture here, and third one here. And if you look at a very sketchy diagram where we've got also the age constraint, we have the 3 events in the last 7 plus or minus 2,000 years. So again, it gives a mean recurrence interval of 4,000 years. This is what we've got comparing the morphotectonic in yellow and the paleoseismology with this area common to the both results. And if we put everything from Bogd and Boulnay, this is what we've got. And of course, you may want to give the priority to the paleoseismic interpretation because they're really the dating of events. Although, as you know, this is also, you've got instances when you do this. We don't have so much data, so I think it's worth to compare the overall results. And to me, this suggests that we do have seismic cluster associating to the Bogd and Boulnay fault in the past. Although, of course, we need to carry out more paleoseismology to better constrain this result. And we do need also to look at the other faults in Mongolia, because there is not only the Bolnai or the Eastern Bogd or the Fuyun, there are many other faults. And actually, I'd like to raise the question of the Fuyun, because Fuyun is also this earthquake that occurred in 1931. We don't have much data about this. These are the slip rates in yellow, horizontal slip rates from morphotectonics along the different faults. In green are the vertical slip rate. And in fact, I just played with the GPS with the help of Philippe Vernon. If you fixed here the Dzungaria here, and you can see that everything turned around, of course, and we have a mean to estimate the maximum right lateral slip rate across the Altai. And if you put in this the constraint from morphology, from morphotectonics, we would have a slip rate across, in Fuyun that would be between 7 actually, which is a maximum again, because there's certainly something inside the Dzungari itself here. But maximum 7 and minimum 1.5. And you see, of course, that if it's 1.5, we may find recurrence time similar to what we've got in Bolnai and Bog, because if you divide a characteristic slip, which is shown by Klinger, Echebes et al. Here, a beautiful 6-meter repetition. If you divide 6 by 1.5, you're going to find a 4,000 years recurrence. But if it's 5 millimeter, of course, this would mean that the Fuyun fault is working much often. I'm going to head with this slide. In terms of paleoseismic records, the other place where we've got results are the western part of the Gobi Altai, so recent work by Robin Kurtz. I've just defended its PhD. And this diagram is synthesizing all what we've got of Gobi Altai, including the eastern part here that I just presented earlier, and also the Bolnai fault. And you see, of course, we've got large uncertainty, so it's difficult to tell whether we do have a clustering. However, what we can see is that all these faults have showing surface rupturing events separated by very long period of quiescence. And the cluster I was mentioning between Bolnai and Eastern Bog was there. So whether we would have here in a 500 years period a huge clustering involving all the Gobi Altai and the Bolnai is a question. There are also a question further in the past. So I think here in Mongolia we have a very good example for studying this question of clustering in a intracontinental setting, and also the mechanism that control them. And this is going to be my last slide. Thank you.